This video is a continuation from the last one. We are now going to be graphing cotangent, cosecant, and secant. So for cotangent, if you recall from the previous unit, cotangent is the reciprocal of tangent. And for reciprocals, wherever tangent crosses the x-axis or has a solution, cotangent will have a vertical asymptote. So for tangent crosses the x-axis at 0 for our snapshot, for the one cycle that we use for our transformation table, which means cotangent will have a vertical asymptote there. And then wherever tangent has a vertical asymptote, cotangent will have an x-intercept or a solution, okay? So I will go ahead and plot that there. So based on tangent, our vertical asymptote here is 0. So the vertical asymptote is at x equals 0. And then because the vertical asymptote for tangent is at pi/2, that means that this point is also at pi/2 for cotangent. Now, typically when I sketch, or for my sketches, you're going to see me start with asymptotes and end with asymptotes. You don't have to do that. However, it does break up the curves that we're looking at, which makes it a little bit more difficult to sketch when we transform them. So if you want to start at -pi/2, you can. Just make sure that your concavities are matching up and that you aren't making mistakes when you're creating your transform sketch, okay? So cotangent and tangent are reciprocals, which means they will have the same period. So that means cotangent will also have a period of pi. So that means the next vertical asymptote will be at x equals pi. And because tangent is always increasing, its reciprocal will always decrease. Therefore, we should see tangent or cotangent look like this. So we'll still be at 1 and -1. So these will be the 5 key points that we use for cotangent. All right, so we'll have the inputs. For cotangent, we're going to go from 0 to pi, and those will be our 2 vertical asymptotes. And then we have that x-intercept at pi/2, so that'll be 0. And then we'll be at -pi/4, and then, I'm sorry, not -pi/4, I'm thinking tangent. That should be pi/4 and 3pi/4. So for tangent's table, we were always increasing. For cotangent's table, we are going to decrease. So you should be going from 1 to -1. All right, so let's go ahead and start with our domain transformations. Now, because we do not have a phase shift, this is okay. Pi/2 times x. We can clearly see that the b value is going to be pi/2. This is different than what we had up here. We had a phase shift that was affected by that too, so we had to factor it out. But since we do not have a phase shift or horizontal shift, we are okay. We can leave it as is. All right, so for our input values, our b value is pi/2, which means we want to multiply the input values with the reciprocal of that, which will be 2 over pi x. All right, we plug in 0, we get 0. Now remember, because our b value has a pi in it, that means our inputs will not be in radians. Okay, so don't be surprised when we see that we end up with no pi in our answer. So now we have 2 over pi times pi/4. Pi's cancel out, so we get 2 over 4, which reduces to 1/2. And we have our interval, okay? So that means we are increasing by 1/2 each time. So I don't even have to do any more multiplication and dividing. I can just follow this. So if I add 1/2 to 1/2, I get 1. Add another 1/2, we get 3/2. Add another 1/2, we get 2. This can save a lot of time. Now, okay, I will be honest. On the AP exam, you will not be asked to do this. You are not asked to sketch on the AP exam, which means you will not have to use a transformation table to this extent. However, remembering, recalling, understanding the attributes. That's why we're doing this. And then in our class for ICA 2, which is coming up, you will be expected to sketch. And then also on the assessment, you will be expected to sketch. But specifically for College Board, you will not be asked to sketch. But we do, just because we want you guys to get used to what these graphs look like, whether they're trends, how are they related. That way it's easier when we do trig, inverse trig, trig identities, everything that's coming forward. Okay, so I promise it's not wasted. Just because it's not on the AP exam doesn't mean it's not important. So with this one, it looks like our inputs, we have range transformations. So let's do those as well. Sorry about that. So we have -3 and +1. So we'll do -3 times y plus 1. All right, so those two vertical asymptotes, they are not changing. We did change them side to side, but vertically they will never change. And then the 1, we plug in 1. We get -3 times 1, which is -3. Add 1, we get -2. Plug in 0, we get 1. Plug in -1, we get 3 plus 1, which is 4. All right, I'm going to go ahead and reduce this so that I have more space. Captured everything. There we go. All right, so I'm going to white out the center part so I don't mix my points up. You don't have to do this, but it makes it easier for me to see what's going on. And we are in quadrants 1 and 4. So I'm going to slide more to the positive x values, or positive input values. So we have 0, we have 1/2, we have 1, 3/2, and we have 2. And then we have -2. Let me bring that down a little bit. Then we have our 1, and then 4. All right. So you might hear the wind or some ice. It's that ice storm that we got. I'm making the videos during the ice storm, so you might hear some random noises in the back, or wintry mixed storm, or whatever they called it. Okay, so for the vertical asymptote, it's going to be at 0. And then we also have one at 2. And then our key points will be at 1/2, -2, 1, 1, and 3/2, 4. And then we'll make sure you're concave down and then concave up. Tangent's a little difficult, if you're like my scaling, I made it too wide. So I'm really trying to emphasize concave down to concave up, which I think I said the opposite before. Okay, so try not to make it look linear. Make it look concave up to or concave down to concave up, so we can see that point of inflection in there. Now, hopefully you realize because we have that vertical reflection, that's going to flip our cotangent. Therefore, it looks like tangent. So you can technically write any cotangent function rule as tangent and vice versa. All right, cosecant. 3 cosecant x minus pi over 2. All right, so let's try our little sketch. So cosecant, I don't memorize the tables. I'm not going to lie. What I do is I rely on the sketch, and then I can pull my points from that. If you do memorize the tables, then go straight to the table, which means you can skip ahead if you want to. So for cosecant, we can use the reciprocal to get our sketch. All right, the reciprocal of cosecant is sine. Remember, they do not share the same first letter. So for sine, I'm going to draw a little, what color? Let's use this one. So this is what sine looks like from before. And what I do with this is that I can think about the relationship between the reciprocals. Okay, anytime that sine crosses the x-axis or has a solution, that means cosecant will have a vertical asymptote. So I'll have a vertical asymptote here, vertical asymptote here, and a vertical asymptote here. And I talk about that a lot in the Unit 11 videos. So if you want to go look at that to see how do we know that, you can see it in that video. All right, and then also we talked about how they will share their relative extrema, okay? So sine and cosecant will share their relative extrema. So that means we have this. So just like tangent and cotangent, how tangent is always increasing, therefore cotangent is always decreasing, you can also see that their concavity changes. So if we look at quadrant 1 for tangent, it is concave up. But if we look at cotangent, sorry, not quadrant 1 specifically, but this part of the curve, it will be concave down for cotangent. Therefore, the concavity will also switch for sine and cosecant. Sine here is concave up, therefore cosecant will be concave down, same over here. Okay, so now from here I can extract the key points for cosecant. And again, I like using asymptote to asymptote. Cosecant doesn't really break up because we're using the sine curve, but for secant, that's going to be a little bit different, but we'll talk about that once we get there. So for sine, this was at negative pi, and we're going to pi again with the 0, negative pi over 2, and pi over 2. So same key points for sine, input-wise. And then we'll have 3 vertical asymptotes. So 1 period for cosecant has 3 vertical asymptotes if you're plotting it this way. All right, negative pi over 2, we will be at negative 1, same as sine. And then pi over 2 will be at 1, same as sine. All right, so we don't have any factoring to do. So let's go ahead and talk about the input transformations. I see that we have x minus pi over 2, so we have a phase shift to the right. So we are going to add pi over 2 to our inputs. So x plus pi over 2. So negative pi plus pi over 2, that's going to give us negative pi over 2. Negative pi over 2 plus pi over 2, we get 0. So now from here, I can see that they are going to be spaced out by pi over 2. So no more plugging in, I can just add pi over 2. So 0 plus pi over 2, we get pi over 2. Pi over 2 plus pi over 2, we get pi. Pi plus pi over 2, we get 3 pi over 2. All right, for the y values, we have a 3. So we're going to multiply the y values by a factor of 3. So vertical dilation with a scale factor of 3. The vertical asymptotes will not change, which means this negative 1 is a relative minimum. That means they are going to be pulled upward. Sorry, we're looking at negative 1, which is the relative maximum. That means it's going to be pulled down by 3. So we'll have negative 3. And then our relative maximums will be pulled up by 3. So that's that vertical stretch taking effect. And again, I forget, there's plenty of space. We can just do it in this bottom corner. All right, so if I look at this, I'm mostly in quadrants 1 and 4, but we do have that negative input. So I'm going to keep a little bit on the negative side. So we'll have negative pi over 2, 0, pi over 2, pi, and 3 pi over 2. And I'm going to white out this middle part. And then our outputs, we have a 3 and a negative 3. So vertical asymptote will be at negative pi over 2, pi over 2, and 3 pi over 2. That relative extrema will be at 0, negative 3, and then pi, positive 3. And again, the concavities are going to go away from the x-axis. It's going to have the opposite effect as sine, where they are going towards the x-axis. And here is our sketch for cosecant, the transformed function of cosecant. All right, next we have secant, the last one for this video. And hopefully you notice right away that we need to factor out this too, okay? So we'll go ahead and do that. So we'll have secant, and I don't know, there should not be, we don't need all of those parentheses. So I'll go ahead and remove them. There. But we will need them for the next part, since now we're trying to isolate the x variable. So I'm going to factor out that 2. So I'm left with x minus, again, multiply with the reciprocal. I think this is the exact same thing we did for, it was either sine or cosine, I can't remember. But we're going to multiply with the reciprocal, which is 1/2, so we end up with pi over 4. All right, so for secant, this is the one that I was talking about while doing cosecant. For secant, I'm going to use cosine. And then leave a little bit more space on the positive side. So cosine looks like this. Actually, this looks weird. Let's scoop back, or go up a little bit quicker. There we go. So these are my 5 key points for cosine. It was the minimum, x-intercept, maximum, x-intercept, minimum. Okay. Wherever cosine crosses the x-axis, secant will have a vertical asymptote. For the same reason that secant has vertical asymptotes for the same reason that cosecant has vertical asymptotes where sine crosses the x-axis. All right, so if I look at this for cotangent, tangent, secant, I always start and end with a vertical asymptote. Okay, but for this one, for secant in particular, I have a little bit left over here, all right, which means when I start my sketch, I'm not starting with a vertical asymptote, I'm starting with one of my relative extrema. And that can get a little bit difficult sketching, but if you don't want to change it, you don't have to. And I talked about this in class, but what I'm going to do is I'm going to stick with my trend of always using the vertical asymptotes first. So the first thing that I want to do is I need to shift over a little bit. I need to find that third x-intercept for cosine so that I can begin with a vertical asymptote and end with a vertical asymptote. So therefore, I am now ignoring what's over here. And then just like sine and cosecant, secant and cosine share their relative extrema. Okay, so now let's get to the table. So cosine starts at negative pi, all right? But because I'm shifting everything over so that I can start with that vertical asymptote, we are going to start with negative pi over 2. And then we're going up by increments of 1/2, so 0, pi over 2. And then for cosine, we stopped with pi, but that's only 4 points. And I need to add that section that I added so that I could end with the vertical asymptote. And I end up with 3 pi over 2. So outputs, vertical asymptotes, occur every pi. And then at 0, we'll have that relative minimum. It's a maximum for cosine, which means it's a minimum for secant. So that's going to be at 1, and then negative 1. All right, so we only have transformations affecting the domain. So I'm going to go ahead and shorten that side. And then I'm going to move this over a little bit. Okay, so as far as the domain, we have a b value of 2, which means we have a horizontal dilation with a scale factor of 1/2. So we're looking at a horizontal compression. So we'll have 1/2 times x, and then we have a phase shift or a horizontal translation of pi over 4. It's minus in our function rule, therefore it is going to be shifted to the right. So we'll do plus pi over 4. All right, so now we'll substituting in for x. So we end up with 1/2 times negative pi over 2 plus pi over 4. So we end up with negative pi over 4 plus pi over 4, so we get 0. Plugging in 0, we just end up with pi over 4. So now we're good. We know what the distance is between each input, so we can just add that much each time. So from 0 to pi over 4, it's pi over 4. If we add pi over 4 to pi over 4, we get pi over 2. Pi over 2 plus pi over 4, 3 pi over 4. 3 pi over 4 plus pi over 4, we get pi. So that saves a lot of time recognizing that, because then you won't have to do so much manipulation. You just have to do it for the first 2 rows. All right, sketching this, it looks like we are in quadrants 1 and 4. So we'll be on the positive side. 0, pi over 4, pi over 2, 3 pi over 4, and pi. So we'll have a vertical, let me do the vertical marks as well. So 1, -1. Vertical asymptote at 0. Vertical asymptote at pi over 2. Vertical asymptote at pi. And then at pi over 4, we have a relative minimum. And then at 3 pi over 4, we have a relative maximum. And they are going away from the x-axis. So again, remember, the definition of a relative minimum is that it is the lowest y value within that neighborhood. And then the definition of a relative maximum is it's the largest y value within that neighborhood, okay? So yes, this value is larger than that one, but when we talk about relative or locally, we only care about what's happening nearby, right? So therefore, this is still considered a minimum, and that is still considered a maximum. All right, hope these videos helped, and we will do writing equations next.